Hello and welcome to Computer Science 4DS. This is Getting to Know Greenfoot, Chapter 1 of the Greenfoot textbook. You can read the first little part there of Chapter 3. We're going to start with where it says 1.1 Getting Started. It says start Greenfoot and open the scenario Leaves and Wombats from the Greenfoot Scenarios folder. You can do this by choosing Scenario Open from the menu. Now you'll probably have these saved elsewhere. You'll have to check with me in class, probably on the school directory, or it could perhaps also be in Dropbox or someplace that I store it. I'm going to open Leaves and Wombats. And you will see your screen looking like this. Let's flip to page 4. Where it says, you will now see the Greenfoot main window with the scenario open, looking similar to figure 1.1. The main window consists of 3 main areas and a couple extra buttons. The main areas are the world. That's what this area is down here, the sand-covered area. Over here on the right, we have the class diagrams. And we have the execution controls down here at the bottom. And we're going to look at each of those in depth right away. So 1.2 objects and classes. We will discuss the class diagram first. The class diagram shows us the classes involved in the scenario. In this case, they are world, wombat world, actor, wombat, and leaf. All of these things over here on the right. We shall be using the Java programming language for our projects. Java is an object-oriented language. The concepts of classes and objects are fundamental in object orientation. And you'll find as we start getting into this that it's sort of similar to Scratch and BYOB. Scratch and BYOB are somewhat related to object-oriented. Liberty Basic is nothing like that. Having said that, you will have to do some actual coding with text here. So you can sort of think of Greenfoot as sort of a combination of Scratch and Liberty Basic. Back to the book. Let's start by looking at the Wombat class. The class Wombat stands for the general concept of a Wombat. It describes all Wombats. So right here, anything that's inside this, any coding that's inside this Wombat refers to every particular Wombat that you're going to create. Once we have a class in Greenfoot, we can create objects from it. Objects are often referred to as instances in programming. The two terms are synonymous. A Wombat, by the way, is an Australian marsupial. If you want to find out more about them, it says you should just go ahead and Google them. So we're going to right click on the Wombat class and you will see the class menu pop up. So we're going to click right click here and this is called the class menu. The first option is new Wombat. So we're going to click new Wombat and then you can put it over here. Now it gets a little bit tedious doing it this way. So if you've got Wombat selected and you hold the shift button down, you can put as many Wombats as you want in the world. Flip the page over to page 6. It says once you have a class in Greenfoot, you can create as many objects from it as you like. And so it says create some more Wombats in the world and create some leaves. So now I'm going to click on leaf and we're going to create a bunch of leaves as well here. Create as many as you want. Put some in front of Wombats, put some behind and some to the side. Okay, so 1.3, interacting with objects. Once we place some objects into the world, we can interact with these objects by right-clicking them. This will pop up an object menu. So let's pick a particular Wombat here, top right-hand corner, and you'll see that you've got this menu. The object menu shows all the operations that this specific object can perform. For example, a Wombat's object menu shows us what this Wombat can do, plus 2 additional functions, inspect and remove, which we shall discuss later. In Java, these operations are called methods. It cannot hurt to get used to standard terminology straight away, so we should also call them methods from now on. We can invoke a method, or I might say call a method, by selecting it from the menu. So these methods are very similar to subroutines and functions. We use the word invoke rather than call. And we're going to talk more about that in the near future. So it says to invoke in exercise 1.2, invoke the move method on a Wombat. What does it do? Try it several times. Invoke the turn left method. Place 2 Wombats into your world and make them face each other. So let's see if we can make some of these guys move. I click this one here and I'm going to say click on move. And you'll notice that he moved over one. Let's see if we can make these 2 guys here face each other. I'm going to make this one turn left. It turns left. This guy, because we don't have turn right, I'm going to have to move 3 lefts. And then I'm going to have to move them. So now they're facing each other. By the way, before I go too much further, you should have a copy of this worksheet that I've created for you just to sort of keep track of everything. So you may want to do this as you go along through the video, or if you want to do it at the end, that's up to you. So you should have taken care of that right now. Exercise 1.2 is right here. Okay, back to the Wombats. So we've moved our Wombats on page 7. In short, we can start to make things happen by creating objects from one of the classes provided. And we can give commands to the objects by invoking their methods. Let's have a closer look at the object menu. The move and turn left methods are listed as void move and void turn left. We can see that the method names are not the only thing shown. There's also the word void at the beginning and a pair of parentheses at the end. These two cryptic bits of information tell us what data goes into the method call and what data comes back to it. So now we're going to talk about 1.4, return types. The word at the beginning is called the return type. It tells us what the method returns to us when we invoke it. The word void means nothing in this context. Methods with a void return type do not return any information. They just carry out their action and then stop. So for example, when I move, it doesn't return any value. It just makes the wombat move. This is very, very similar to a subroutine in Liberty Basic. Back to the book on page 7. Any word other than void tells us that the method returns some information when invoked and of what type that information is. In the wombat's menu, we can see that the words int and boolean. The word int is for integer and refers to whole numbers, numbers without a decimal point. Examples of integer numbers are 3, 42, -3, and 120 million. The type boolean has only two possible values, true and false. A method that returns a boolean will return either their value true or their value false to us. These are very similar to what I created when we talked about Liberty Basic. And I created these notes here and then decided against it, but it's good for this purpose. Here's a small little function from Liberty Basic, function numcheck. So this type of function here has returned a value. It's going to be either true or false. BYOB blocks we had as well, okay? And they can be predicates as return a true or false, or they can return a number. So these are like functions once again. Back to the book. Methods with void return types are like commands for our wombat. If we invoke the turn left method, the wombat obeys and turns left. Methods with non-void return types are like questions. Consider the can move method, boolean can move. When we invoke this method, we see a result similar to that shown in figure 1.5, displayed in a dialog box. The important information here is the word true, which was returned by this method call. In effect, we have just asked the wombat, can you move? And the wombat has answered by saying yes. So exercise 1.3, invoke the can't move method on your wombat. Does it always return true, or can you find situations in which it returns false? So all of these guys here, if you go can move, will say true. Even this guy here, who's bumped up against this guy, also true. So can you come up with a situation where they can't move? I'll let you try that out for a minute. I suggest you pause the video, and then I'll give you the answer. All right, so hopefully you paused the video and tried that out for yourself, and you should have discovered that when you put the wombat right up against the wall, the edge of the world, and you click can't move, it returns false. Okay, so top of page 8. Try out another method with the return value. So int get leaves eaten. Using this method, we can get the information how many leaves this wombat has eaten. So let's just check one here, and you'll see that the number of leaves that are eaten here are 0. This is a variable here, the number of leaves eaten. So let's return the value 0. Using this method, we can get the information of how many leaves this wombat has eaten. Exercise 1.4. Using a newly created wombat, the get leaves eaten method will always return a 0. Can you create a situation in which the result of this method is not 0? In other words, can you make the wombat eat some leaves? And I'm going to show you how to do that. You try it on your own, pause the video, and then come back for the answer. Okay, so hopefully you figured out how to make that work. If you put the wombat in front of a leaf and you get him to eat a leaf and then check the number of leaves eaten, still 0. What has to happen is the wombat has to be right on top. Make him eat a leaf. The leaf disappears. Number of leaves eaten is now 1. So they have to be on top of one another. Back to the book on page 8. Methods with non-void return types usually just tell us something about the object. Can it move and how many leaves it has eaten? But do not change the object. The wombat is just as it was before we asked about the leaves. Methods with void return types are usually commands to the object to make it do something. Parameters. The other bit in the method menu that we've not yet discussed is the parenthesis after the method name. The parentheses after the method name hold the parameter list. This tells us whether the method requires any additional information to run, and if so, what kind of information. If we see only a pair of parentheses without anything else in it, as we've seen in all methods so far, then the method has what we call an empty parameter list. In other words, it expects no parameters. When we invoke the method, it will just run. If there's anything between the parentheses, then the method expects one or more parameters, additional information that we need to provide. Now let's go back to those notes that I showed up before. So when you've got a little box in BYOB, it's expecting a parameter, expecting a number. Function numCheck is expecting two parameters, the x and the num overstring. Same idea. Let's try out the set direction method. We can see that it has words int direction written in its parameter list. When we invoke it, we see a dialog box similar to the one shown in 1.6. Now on the top of page 9, that's a Macintosh version. Let me just show you what it looks like in Windows. So I'm going to go set direction, and you get something that looks like this. The words int direction tells us this method expects one parameter type int, which specifies a direction. A parameter is an additional bit of data we must provide for this method to run. Every parameter is defined by two words. First, the parameter type, here it's an integer, and then a name, which gives us a hint what this parameter is used for. If the method has a parameter, then we must provide this additional information when we invoke or call the method. In this case, the type int tells us that we should now provide a whole number, and the name suggests that this number somehow specifies the direction to turn to. At the top of the dialog is a comment that tells us a little bit more. The direction parameter should be between 0 and 3. So you will notice here, and I had it in my notes that I was creating for you and then decided not to, notice the comment in the method documentation. So once again, comments are important. Here we have, if we didn't know that it should be in the range 0 to 3, we as the user would have no idea what number to put in there. So let's try in exercise 1.5. It says invoke the set direction method, provide a parameter value and see what happens. What number corresponds to which direction? Write them down. What happens when you type in a number greater than 3? What happens if you provide input that's not a whole number, such as a decimal value like 2.5? So go ahead and try that. If we put in 0, I've forgotten which wombat I'm looking at here, but you can mess around with that. Set direction, okay? See what happens when you put 1 in, and so on. It looks, he moved down like that. Keep in mind that this question is also over here on your worksheet. So play around with that, pause the video, and then unpause when you're ready to move on. Reading on page 9 now. The set direction method expects only a single parameter. Later, we shall see cases where methods expect more than one parameter. In that case, the method will list all the parameters it expects between the parentheses. The description of each method shown in the object menu, including the return type, method name, and the parameter list is called the method signature. So that's what this is. This is the method signature. We've now reached a point where you can do the main interactions with Greenfoot objects. You can create objects from classes, interpret the method signatures, and invoke methods with and without parameters. Okay, bottom of page 9, Greenfoot execution. There's one other way of interacting with Greenfoot objects, the execution controls. So if you flip the page now to page 10, exercise 1.6 says place a wombat and a good number of leaves into the world and then invoke a wombat's act method several times. What does this method do? How does it differ from the move method? Make sure to try different situations. For example, the wombat pacing the edge of the world or sitting on a leaf. So try it out. And let's just go this guy right here, and I'm going to go act. And you'll notice that he moved over, didn't do anything when he got there. But now when I ran act, he actually ate him, and he keeps moving. I'm not sure what's going to happen there. Notice that when he gets to the edge, oh, he ate that leaf. Now he's turning left. Okay, so act and move are slightly different. So pause the video here and just jot that down on your worksheet. Now, I would like you to click the act button in the execution controls near the bottom of the agreement. What does this do? So let's go back to, let's pick this guy right here, and let's go act. And you'll notice that all of the wombats start to move. Okay, play around with that and play around with the run button. And you'll notice that when you hit run, it basically does act over and over again. So you should enter that information on your worksheet. Pause. What do you think happens if I hit reset? As expected, it completely resets. So we're going to have to create a whole bunch of new leaves and a whole bunch of new wombats. Like so. Okay, back to page 10. It gives you the answers to those questions right there, and you can read through that on your own. Moving now to 1.7. Open another scenario named asteroids from the chapter 1 folder of the book. Book scenarios, it should look similar to figure 1.7. And again, you'll have to likely get these off the iDrive or Dropbox or somewhere, wherever I've stored them for your particular class. Okay, and here's my asteroids version. Okay, 1.8, understanding the class diagram. Let us first have a closer look at the class diagram. At the top, you see the two classes called world and space connected by an arrow. The world class is always there in all Greenfoot scenarios. It's built into Greenfoot. The class under its space, in this case, represents the specific world for this particular scenario. It's up here in the right-hand corner. Its name can be different in each scenario, but every scenario will have a specific world here. Page 12. The arrow shows an is-a relationship. Space is a world in the sense of Greenfoot worlds. Space here is a specific Greenfoot world. We also sometimes say that space is a subclass of world. We do not usually need to create objects of world classes. Greenfoot does that for us. When we open a scenario, Greenfoot automatically creates an object of the world subclass. The object is then shown on the main part of the screen. The big black image of space is an object of the space class. And you can change your space as a subclass, and you can change its image, you can change its various parameters. And if you right click on it, and I'm not going to show you that just yet, but you can change various things about that. Below this, we see another group of 6 classes linked by arrows. Each class represents its own objects. Reading from the bottom, we see that we have asteroids, rockets, and bullets, which are all movers, while movers and explosions are actors. You can see that here. Bullets, asteroids, rockets are movers. Explosions are actors, as are movers. Again, we have a subclass relationship. Rocket, for example, is a subclass of mover. Rocket is a mover. And mover and explosion are subclasses of actor. Mover is an actor. Conversely, we say that mover is a superclass of rocket, and actor is a superclass of explosion. Subclass relationships can go on for several levels. Rocket, for example, is also a subclass of actor because it is a subclass of mover, which is a subclass of actor. We shall discuss more about the meaning of subclasses and superclasses later, but this idea, this hierarchy here, is a very important idea in Java and a very important idea in object-oriented programming. The class vector shown at the bottom of the diagram under the heading Other Classes is a helper class used by other classes. We cannot place objects of it into the world. So down here is vector, and it basically stores methods. That's sort of like a library of various methods that can be stored down there. Okay, let's actually play with some asteroids. 1.9. We can start playing with this scenario by creating some actor objects of subclass of actor, and place them into the world. Here we create objects only of the classes that have no further subclasses: rocket, bullet, asteroid, and explosion. Let's start by placing a rocket and 2 asteroids into space. Remember, you can create objects by right-clicking on the class and selecting the class, and then shift-clicking. So let's create 2 asteroids and 1 rocket, like so. When you've placed your objects, click Run. You can then control the spacecraft with the arrow keys on your keyboard, and you can fire a shot by using the spacebar. Try getting rid of the asteroids before you crash into them. Now, I should point out that I played this game way back in the 80s, but I'm a little bit out of practice, so I will likely die. Okay, and you can play around with this, and you will notice that it would sure be nice. You can go forward. It would sure be nice if you could shoot a little faster. Let's click pause. Exercise 1.10. If you played this game for a bit, you will notice you cannot fire very quickly. Let's tweak our spaceship firing software a bit so we can shoot more quickly. This should make getting rid of the asteroids a bit easier. Place a rocket into the roll and then invoke its set gun reload time method through the object menu and set the reload time to 5. Play again with at least 2 asteroids to try and find out. So we're going to click here, and I'm going to set the gun reload time. You'll notice that, again, I'm going to point out in the comment, the initial standard time is 20. So let's set it to 5, and now let's run. And now you'll notice that I can shoot a whole lot faster. I still died. Now it's important to note that if I bring in a new rocket here, that the reload time on it is back to 20. So every time you die, you're going to have to reset that back to 5, which is not very good. Oh, I just died in the middle of that. Let's just run that. Pause, create a new rocket, and then set that gun reload time back to 5. Now, obviously, that's not very good. I'm going to show you how to fix that a little bit later in the chapter. Okay, exercise 1.11. Once you've managed to remove all asteroids or at any other point in the game, you can stop the execution. I showed you how to do that by pressing pause and find out how many shots you fired. So let's just fire some shots here because I just created that new guy. And then click pause, right click, int get shots fired. So it's going to ask, and it's going to return a value, how many shots have you fired? And it turns out I've fired 10. So there's a variable that's been created. Exercise 1.12. You will notice that the rocket moves a bit as soon as you place it into the world. What is its initial speed? Now, unfortunately, in the time that the book has been created and the scenarios have been created, there's been a bit of an update, and I wasn't actually able to find the speed. I tried. You'll notice in the teacher manual that I have, it shows that there's a method called get speed, but it's not here. But you will notice that this rocket, because he has inherited from actor and inherited from mover, all of these methods are available as well. So there isn't actually, there's a move, there is no get speed that I can see. There's one for increase speed. There's one for get movement, but it returns a vector. So, and it's not really a physics vector. So they've made a slight little change there. So we're going to be unable to determine the actual speed of the rocket. However, at the top of page 13, exercise 1.13, asteroids have an inherent stability. Each time they get hit by a bullet, their stability decreases. When it breaks to zero, when it reaches zero, they break up. What is their initial stability value after you create them? By how much does the stability decrease from a single hit by a bullet? So let's just reset. I'm going to create a single rocket and a single asteroid. And we'll notice here that the stability is 64. So let me just run this here and see if I can shoot that guy once. And I'm down to that, shooting it. You'll notice that, okay, so now they're at 20. So I broke them into part. And so now let's get the stability. And you'll notice that he's down to 32. So every time we hit, it divides by 2 the stability. And that basically is the size. So in exercise 1.14, you should make a very big asteroid. So these are size 32. So if we want a really big asteroid, new asteroid in size, and I gave it 100. Notice here in the comments, they didn't give you the actual size, which is unfortunate. They should have done that. Now I get a really big asteroid. And let me just see if I run here and try to get this guy. Oh, look out. Oh, that was a mistake. New rocket. Oh, let's have hit the pause. New rocket. There we go. Now run. Good one. Now let's just see how big those guys are. They should have a size of, oh, wrong one. They have a size of 50. So you can see it's a divide by 2 relationship. All right, so now on page 13 here, 1.10 source code. The behavior of each object is defined by its class. The way we can specify this behavior is by writing source code in the Java programming language. The source code of a class is the code that specifies all the details about the class and its objects. Selecting Open Editor from the class's menu will show us an editor window that contains the class source code. The source code for this class is fairly complex, and we do not need to understand it all at this stage. However, you study the rest of the book and program your own games or simulations, you will learn over time how to write this code. And you can see the picture of it there on page 13. Go to page 14. At this point, it's only important to understand that we can change the behavior of the objects by changing the class's source code. Let's try this out. We've seen before that the default firing speed of the rocket was fairly slow. We could change this for every rocket individually by invoking a method on each new rocket. But we would have to do this over and over again every time we started playing. Instead, we can change the code of the rocket so that its initial firing speed is changed, say to 5, so that all rockets in the future start with this improved behavior. Open the editor for the rocket class. About 5 lines from the top, you should find a line that reads gun reload time equals 20. So to do that, we're going to click here on rocket. We're going to open the editor, and here is the source code for that. Just get my recording window out of the way. You can make it a little wider if you want. Notice all the comments. Comments are important. Notice also that all of the variables that are here also have a definition, what it's for. gun reload time is 20, so you can go ahead and change that to 5. You'll have to save that to your own H drive. Please do not save to the I drive. This is where the initial gun reloading time gets set. Change this line so that it reads gun reload time equals 5. Be sure to change nothing else. You will notice very soon that the programming systems are very fussy. A single incorrect or missing character can lead to errors. If, for example, you remove the semicolon, you would run into an error fairly soon. So let's just change this to a 5. And I'm going to remove the semicolon and then click somewhere else. You'll notice here, it's already saved the file. There's a little underline here, and you'll notice that it tells you what's expected. So a much smarter sort of error handling thing. It usually tells you what the problem is. So put that in there. Now, if you close this, you see these stripes here, okay? And this tells us that we've made a change, and we have to actually compile it. Now, at times, I've found that it will actually compile it automatically for me. I don't think you can run this. You notice you can't run it. And there it's gone. It's compiled it by itself. Okay. The other way to do this compilation, and I'm just going to read here on page 14. Second last paragraph. Close the editor window and look at the class diagram again. It has changed. The rocket class now appears striped. The striped look indicates that the class has been edited and now must be compiled. So I think what's happened in the time that the book has been published, and this is the very latest version of Greenfoot, I think they've made it an auto compilation. So you don't have to do that, apparently. Maybe you do. Compilation is a translation process. The course's source code is translated into machine code that your computer can execute. So the other way to do that is if you go back into here, if you double click there, by the way, it opens that up. So if I set that back to 20, and then you click compile, it will translate that all to machine code. It tells you down here you have no syntax errors. You can close. Notice that the stripes went away right away, and we could run it, but I didn't put anything in there yet. Reading now on page 14. Classes must always be compiled after their source code has been changed before new objects of the class can be created. Sometimes several classes need recompilation even though we've changed only a single class. This may be the case because classes depend on each other. When one changes, several may need to be translated again. So you're going to learn more about that, and you're going to figure that out on your own. Again, I think they've got an auto compile in there. We can compile the classes by clicking the compile button in the bottom right-hand corner, which I don't see anymore. Once a class has been compiled, the stripes disappear and we can create objects again. Okay, so exercise 1.15, make the change to the rocket class source code as described above, close the editor, and then compile the classes. Try it out. Rocket should now be able to fire quickly right from the start. We're going to come back to the asteroids game in chapter 7. For now, though, let's just quickly look at the summary on page 15. I'm not going to read it. We've gone through the whole chapter. I will point out that what you should know at the end of this is the concept summary. So you can read that there. Greenfoot scenarios consist of a set of classes. Those are the things that I expect you to know by the end of this lesson. So if you've done all that and you've completed your little worksheet, you're going to hand that in just to sort of get a check mark that you've completed it. And if you have time left, then go ahead and play with asteroids. And you can mess around with this. You could probably change something if you want to set how fast the bullets move. You can play around with this as much as you want. All right, have a good day. And I'll be speaking to you again when we talk about chapter 2.